My name is Venkat Guruswamy. I'm a senior scientist at the Simons Institute, and it gives me great pleasure to welcome you all for the boot camp of the data-driven program. I'll keep it pretty brief. Brief history for those who may not know, the Simons Institute was born in 2012, 10 years ago, thanks to a generous grant from the Simons Foundation. And it has ever since hosted basically 2 programs every semester on topics related to theory of computation, but also its interface with all areas in science, engineering, humanities, economics, you name it. So it's really been setting the agenda for the field, and so many people have come through here. And recently it has also expanded its activities to summer programs, summer clusters, and all sorts of outreach activities as well. The Institute just celebrated its 10th birthday in May, and there was a big symposium celebrating that. And I guess in terms of programs, the first program was in fall 2013. So I guess this marks the first program in the 10th year of scientific programs of the Institute. So no pressure. So I'm sure it's going to be a great program. And there'll be a parallel program, of course, which will have its boot camp, I think, next week. Just very few logistical things. I think the schedule is out there. The coffee breaks are going to be, sometimes we have it outside, but now we're going to start out in the area where you were just there. And one kind request, please, finish your coffees and snacks outside. I think we have sort of a water in bottles is okay, but no drinks policy inside the auditorium keeps it clean for everyone. Other than that, I don't think there's anything specific. We have staff and others always on crew if you need something. And I wish you all a very successful boot camp and program.
So it seems I'm giving the first talk of the first workshop of the first program or something. No pressure. All right. So I'm Shipra Agrawal, and I'm one of the co-organizers of this program, and really delighted to see you all here. And thanks, Sid, for organizing the boot camp with his co-organizers. And so I will be introducing stochastic multi-arm bandits. It will be a 2-part introduction of 1 hour each. And the general theme of today, I believe, is based on bandits. So we'll see more information about bandits going further. So let's get started. So what is this topic about? And you will see more of this theme going forward today, later in other talks, and tomorrow as well. Overall, it's about learning from sequential interactions. So when we make decisions that interact with people and collect data, and we make them sequentially so that the data collected from the past decisions and the response is used in future to make better decisions. So for example, think about online retail, where you are presenting some options to customers that they can purchase, and you observe what they purchase, and that gives you, or purchased or interacted with, and that gives you some data that you can use in future in going forward to make more decisions. That gives you more data, and so on. Same way, you can think about ad placements, movie recommendations, and more classic applications like clinical trials, where you collect data from the results of trials on patients to improve the trials or infer something about future trials. And same way in reinforcement learning applications like robotic manipulations, and so on. So what's common among these is that decisions are serving 2 purposes now. So one is the usual purpose, which is you have some kind of objective like immediate reward, clicks, conversions, purchases that you want to maximize. But there's also another purpose, which is to collect data. So you're also thinking about what is the information that these decisions are providing you beyond just the immediate reward or the immediate clicks and conversions and so on. So the information could be of the type like, what did the customer not like, right? So even if it failed in terms of generating a click, it might have succeeded in providing you some information about their preferences. So there is as in life, there's always a trade-off between what you want for now and what you want for future. So there is usually a trade-off between selecting decisions for the information they provide versus the immediate reward they provide. And this trade-off is what you will see repeatedly in many of the topics related to this, which is the trade-off between learning and optimization, between exploration and exploitation. And to formalize this trade-off, we'll start today with the very classic and relatively simple formulation called multi-arm bandits. So the name of this problem, which is formulated long back, comes from this idea of a casino. And just indulge me for a bit as I go through this casino example. You might have seen it before. So imagine you have $100 and you walk into a casino which has 10 different machines, and you want to decide where to put your money. All these machines are rigged in different ways, but you don't know which machine is better than the others. And the only way to find out about a particular machine is to play it. There is no other information available to you. And now every time you play, you have to put $1 in it. So now you have to decide how to use your $100 in the most wise way. Obviously, your goal is to get out with as many as possible in the end. So you could either use your $100 and just randomly play on all the machines, or you could first randomly play for $50, learn about the machines, and then play the machine that you found to be the best among the 10. Or you could do something more adaptive. You could put like $2 in every machine, then narrow down to a few machines, put more money in that, then narrow down to a few machines which look better, and so on and so forth. So you have to decide how to divide your money between exploration and exploitation. That's why you will have this trade-off, whether to learn more or to just use your current information and exploit that information all the time. So more formally, we think about stochastic multi-arm bandit. And here in this talk, my talk, I will focus on the stochastic multi-arm bandit problem, specifically this version of the problem. Later on in the day, you will see other formulations like adversarial, combination of stochastic and adversarial, and so on. So in the stochastic multi-arm bandit problem, we think about discrete rounds, discrete capital T rounds. In every round, you have to pull one out of some n discrete arms. So this is the basic version. We will extend it later to more general versions. One out of n discrete arms. And every time you pick an arm, a reward is generated. So this is one of the key assumptions. Reward is generated IID for that arm, independent of other arms and independent of time, from a fixed but unknown distribution. And we assume bounded support. Again, there are generalization to unbounded support depending on assumptions made. So one of the key things that we call bandit is some kind of information restriction to what you play, right? So here in this version, we will assume that you only observe the reward of the arm you pull, and you don't learn anything about the other arms, which means like if I put $1 on one machine, I only get information about that machine. I don't learn anything about other machines. Again, we will generalize this assumption so that you can learn a little bit about others and so on. Okay. So in this basic version, we are thinking about regret. Regret is how much I could have made if I knew which is the best machine, right? So if I knew what is the best arm in terms of expected reward. So every arm has a mean mu I, expected reward mu I, and the best thing you can do in terms of expected reward maximization is to pull the arm with the highest mu all the time. And if you pull something else, regret is the difference between what you got in expectation versus what the best play was. So here the expectation, I have already taken mu off the arm I pulled, IT is the arm I pulled, but the expectation is over my choice of IT, which depends on my previous plays and so on. So before we move on to kind of diving deep into this formulation, I just want to mention another formulation of stochastic bandit problem, which was in fact what you would have thought of as bandit before machine learning people got into it, basically. So the classic meaning of bandit is a slightly different formulation or slightly different way of thinking about the problem, which is called the Bayesian bandit. So the idea there is that you have a prior distribution on the unknown parameter, which is the mean, let's say, or the distribution of every arm, of the reward distribution of every arm. So you know this prior distribution, and every time you play the arm, the distribution, your belief about this arm's mean evolves. For example, you may think that every arm has a Bernoulli distribution with mean mu I. You don't know mu I, but you have a belief about mu I. And every time you observe something from this arm, your belief about μi changes according to Bayes' rule. Okay, so now you can think about how should I play the arms so that not only I get a good reward in every step, but also my belief evolves fast enough so that I know more and more about every arm. So you can kind of lay out the whole tree, which is, if I start from this prior distribution, if I play in this way, this will be my beliefs at these times, and I can lay out the expected total reward over all capital T time steps. So this is a stochastic process for which you have complete knowledge of how it evolves. But of course, it's a difficult problem to find out what's the optimal policy of this for this stochastic decision process. Okay, so this version of the problem considers what is the optimal policy. Let's find out what is the optimal policy for this stochastic process. So it's overall a stochastic optimization problem in this setting. And this is a very hard problem. It's not a data-driven problem in the way we define it right now, but it is still a very difficult stochastic optimization problem. And a celebrated result by John C. Giddens in 1979 showed that for certain discounted settings, you actually have an optimal policy that you can compute, and you know exactly what to do in every time steps in the optimal way. And this is very important. This kind of solutions are very important, especially when you don't have big data, right? If you have a clinical trial setting with only 100 trials or very few trials, then you maybe want to do the optimal thing and not want to minimize regret and so on. So more recently, there is also work in regret kind of framework for this problem, where you're not looking for optimal policy, but still trying to minimize regret, but you have a prior distribution still, so you can do better potentially. And I will not go through these works today, but this is something for your reference if you're interested in this setting. So this is just my tribute to this important field, but if you want to know more, yeah.
Can you tell us a little bit more why, if the prior is just if you have no prior, why this is not the same as the other one? Optimize the expected.
This one or
you
this
also
one?
optimize the capital.
This one, yeah. So it is the same. It's just that the focus is on finding the optimal policy, which is very difficult in most cases. So this you can only do it in certain specific cases. But it is the same if you know the prior. Yeah. So these two are exactly the same.
But it's also the same you presented before, right?
There we don't know the prior.
Right. So if you don't know the prior, it's exactly the same.
Yes. Yes. So the problem essentially is the same, except that first we don't know the prior. Second, finding the optimal policy is very hard in most cases, except for specific cases where there is index zero policy. Yeah.
I'm thinking about the data selection or a stationary setting where you have some steady state.
Which setting?
Is it like a stationary setting where like
it's not station. I don't assume.
There's something that shouldn't.
So the Giddens index is available for discounted reward setting. So if you discount the reward and total reward is not the sum but discounted, then it's available, but not in it. So I will not go back to that again, but feel free to discuss more in the break about it if you are interested. So what I will talk about is the algorithmic techniques for the version I discussed, the stochastic multi-arm bandit problem, where we don't know the prior and we want to minimize regret. So the way we treat it would be basically to focusing on, can we have a regret that doesn't grow linearly with time compared to the optimal action. And I'll discuss two techniques, UCB and Thompson sampling, and then generalizations of the problem to remove some of the strict assumptions we made. And later on tomorrow, I believe you will see some of these techniques being used for Markov decision process, reinforcement learning, and so on. This is to refresh your memory of what my problem definition was. I'm just flashing this slide once so that you can recall the notations. Okay. So what is the issue here? So I refer to the issue a little bit as, well, I want to balance exploration, exploitation. I want to collect information, not just use the information I have. But let's concretize this in terms of theory, like where does it break if I don't explore? What breaks, right? So here's a very simple toy example. Let's say you have the multi-arm bandit problem with two arms, one let's call a black arm and a red arm, and the black arm is better. Of course, you don't know it. Black arm has a mean 1.1, the red arm has mean 1. And you don't know anything about this mean. The optimal, if you knew what is better, you would play black arm all the time and you will get 1.1 times t. Now, what would be the exploit only strategy, in the sense that if you didn't care about learning or collecting data in a better way, then the exploit only strategy, the typical machine learning strategy would be, let's look at all the data we have, find out the best estimate, the best predictor of the mean of each arm, and let's play the arm with the better mean. Let's say maximum likelihood estimate or empirical mean, which is the best estimate of the mean. And then let's play the arm with the better mean, because that will maximize the immediate reward of the next play, okay? So if you keep doing that, what can go wrong? So here is an example of what can go wrong with a very constant probability almost. So let's say you did something initially, and you are in this kind of stage where you have played the black arm for a few times, the red arm for a few times, and these are the outcomes. Let's assume for simplicity, the red arm is actually deterministic. It always gives you 1. So problem is easier. You don't have to learn anything about the red arm, okay? So you are at this stage, 3 trials of each arm, and they are giving you this. So it can happen, even though the black arm has mean 1.1, it can happen with a constant probability that right now with 3 plays, its mean falls below 1, okay? So right now the mean is below 1 for the black arm, the mean is 1 for the red arm. So now what will happen, according to your best estimate strategy, you would play the red arm for now, because it seems to have a better mean. And that's fine. In machine learning, we do make a mistake sometimes if we don't have enough data. But what goes wrong is that because of that, you play the red arm and you get another sample of red arm, which is useless. You didn't learn anything new. You already knew red arm has mean 1. Then again, you calculate the mean, the situation remains the same. You will play red arm again, and you will keep doing that endlessly. So the problem is, not only you made a mistake, you have no way to correct your mistake because you don't learn anything from playing this arm. And your exploit only strategy keeps asking you to play that same arm to maximize the immediate reward. So to get out of this situation, you have to kind of do some exploration. So you have to say that even though right now this arm seems best, but I don't have enough plays of black arm to trust it, so I need to collect some more data about it and explore it. And this is what we call the exploration exploitation trade-off. We have to choose between playing the best arm according to the current data, which appears to be best for the next step, versus playing the less explored arms or less explored options to make sure that we have good empirical estimates going forward. Okay. And this has to be done carefully, because if you don't have 2 arms, if you have a lot of arms, later on we'll see infinite number of arms, then you have to explore not too much, but not too less either. Okay. So what is the best we can do, at least in this simple problem? So do we know, is there a way to completely avoid mistakes, in the sense of, can we get away from not playing the bad arm at all? Or is there some minimum that you have to do? So you can imagine information theoretically, there has to be a minimum number of mistakes. If you don't have any prior information, as we assumed here, if you don't know anything, you don't have any prior on the arms, then you have to, and you can only learn by playing them, then information theoretically, there is a minimum number of times you'll have to play all the arms in order to figure out which is the best arms. And in fact, there is a very strong lower bound given by Loy and Robbins in their 1985 work, where they show that for any instance, so this is not like there exists some instance which is really bad. They show that for any given instance of the problem, and by instance, I'm defining the distributions of the arms that you fix the reward distribution. For any instance of the problem, any reasonable algorithm, and what does reasonable means is you cannot say that just play ARM2 all the time because it will be optimal for some instance, So that is not any reasonable meaning. They have a particular definition of reasonable. It means that it should work, at least it should converge for all the instances, okay? It should be an algorithm, not just a deterministic play or something. So for any such algorithm, you will play any suboptimal arm at least log t times. And in fact, they give exact constants, which we'll discuss later. Okay, so they give exact dependence on the parameters of the problem. Okay. Yeah.
So you're assuming that the arms are stochastic, as in if they were deterministic, I could just play every arm one.
Yeah. So the idea is that the constants here that I'm referring to, they are basically about how much information there is in the distribution. So there's also a worst case bound. So if you want to say, okay, I don't want to think about the particular distribution or something, you can also show that there exists a bad instance. So that's more like a traditional bound where you say for every algorithm, there exists some instance with square root NT regret. Okay. So here there is no dependence on the parameters of the distribution or anything. So what we will try to do is show some algorithms now which can achieve this lower bound, both the instance specific. So the instance specific logarithmic bound will have dependence on the instance parameters, whereas the instance free square root NT bound will not have any dependence on the parameter of the instance. So first algorithm is the UCB algorithm, and this might be one of the most popular techniques right now in multi-arm bandits, at least in theory. And it's a very nice, simple idea, but it works beautifully, and the proof is quite simple. So the idea is, think about exploration, exploitation in terms of these two terms when making decisions. So firstly, whenever we pull the arm, we get a reward. So based on that, you can compute an empirical mean for every arm. So that's what you would have been doing if you were just caring about exploitation. You would just play according to the highest empirical mean. Okay. So this crazy looking expression is nothing but saying, take the average of the rewards on the time step where you played the arm. Okay. And now when you make a decision, don't make it based on the empirical mean, but boost every empirical mean by the uncertainty in that arm. So even if an empirical mean is small, but if the arm has not been played enough, so NIT is the number of times the arm has been played so far. So if that is small, you kind of give it a boost. So you're saying, if I don't know enough about the arm, I'm going to give it some benefit of doubt, and I'm going to boost its estimate. So the collective estimate developed here is called the upper confidence bound, because the way it's constructed is this is exactly the error bound that you would get from applying a Chernoff bound or a Azuma-Hofding bound on the empirical mean. So this is the error of mu hat IT versus mu I, and you can show this is smaller than 4 log t over NIT, if NIT is the number of samples available, with probability 1 over 1 minus t squared. Okay, so this is a high probability bound on the error, and you have added that error to the estimate, which means that your UCB is always above the true mean with high probability. So it's an upper confidence bound on the mean, and this algorithm simply says at every time step, just play according to the highest upper confidence bound. Okay. And why does this work? So the overall algorithm is simply this: every time pull the arm with the highest upper confidence bound, and then update the upper confidence bounds according to the sample observed. Initially, you kind of do a little play every arm once. This is just to make sure that this is your estimates are well defined and so on. But let's not worry about that for now. So let's see why does this work. So how do we show that it has a small regret? So regret recall is simply the difference. So delta IT, I'm defining the gap between the best mu star versus my mu I. So the regret is simply the delta, the regret of playing every arm at time t, okay, this gap. So you can also think about this as saying that it's delta for every arm I, delta I is the regret for playing arm I, then it's delta I times expected number of times I played that arm by mistake, okay? So to bound the regret by log t, so my goal here would be to bound the regret by sum over I not equal I star log t over delta I. So this is in fact very close to the lower bound given by Lai-Robbins. So instead of delta I, they have KL divergence there. So they have, instead of their bound is close to, so their bound is log delta I log t over the KL divergence between delta between the optimal and the ith distribution. But since KL divergence can depend on the entire distribution and not just the mean, this is kind of harder to write if you don't have specific form of distribution. So a good approximation to delta I over KL divergence is 1 over delta I. So achieving this is basically almost the best you can do in terms of instance specific regret. Okay, so to prove this kind of bound, now looking at this expression here, to prove this kind of bound, I essentially have to prove that the number of times I play an arm I, which is not optimal, can be bounded by log t over delta I squared. Okay, so I want to prove this bound on the mistakes, but the number of times I play an arm I by mistake. Okay. So that will give me the entire regret bound that I want, right? So now let's just focus on proving that you would not play an arm I more than this many times in expectation. So, and this proof is quite simple. So let me. So think about what is the main thing that we observe? We observe that every mu I is smaller than UCB I at time t. So this was the basis of our whole formulation, right? So we always use UCB, the upper confidence bound, with which high probability is more than the actual mean, which also mean that mu star is smaller than UCB of the optimal arm. Okay. Now for an arm to be played, we want to show that a suboptimal arm I will not be played after more than some constant times delta I squared steps. So let's assume Ni at time t is more than this. Number of times it has already been played is more than this. Okay. So let's say we are given this. So now I want to say that, okay, I played it already this many times. Now I will not play it. So what will make me play an arm I at this point? So for an arm I to be played, its UCB must be greater than UCB of the optimal arm. But let's look at the UCB of arm I. We know that it has to be smaller than mu hat I plus, this is how we developed the UCB, right? So this was the formulation of UCB. So in fact, it's equal to that. But I know that mu hat I is smaller than mu I plus that same thing. Right? Because this is from any concentration like Chernoff-Hovding bounds or something, okay? So I know that. Now let's look at this expression. Now think about this C, that C over there. Let's just put that as 16. You can get stronger bounds, but I don't want to go into using more tighter inequalities. So if you put that there, this would become delta I over 2. And this will become delta I over 2. And so this is equal to mu I plus delta, which is actually exactly equal to mu star. So after these many plays, basically your estimates are tight enough so that your error is not enough to make mu I exceed mu star. Okay, so it's smaller than the gap between mu I and mu star. So your upper confidence bound for the arm I is below mu star. And for I star, irrespective of how bad your estimate for optimal arm is, it's always above its own mean. So this is always, so at this point, this is less than UCB of I star. So as a result, you have that UCB of the optimal arm will exceed arm I and it will not be played anymore. Okay. So this shows that after these many plays, you cannot play arm I. And this is all with high probability because the concentration bounds are holding with high probability. So if you can bound the number of plays by this much, we get our regret bound of the desired formulation. Okay. Any questions? Yeah. Mm-hmm.
Repeat the question.
This one? Oh, the question was, can you replace this T here? Oh, sorry, this is the T, little t here in the log by NIT. So you the probability that you will get is this. Yeah, probably like you can do something like that to get tighter bound. I don't know how much the bound will improve. Might improve by yeah, if you care about the logarithmic terms, yeah. So right now there is a, yeah, I'm not sure if that will give you much better order, but if it might give you something in constants, yeah, yeah.
Because you need a warm up at the beginning, right? So you can't.
Yeah, so you'll have to technically, like you'll have to do a few things, like because NIT can be very small in general. So you'll have to do a few initial trials to make sure NIT is not too small to begin with for any arm. Yeah, so you'll have to be careful about it. Yeah. Also, NIT is like not a constant. So yeah, when you're applying the concentration bound, you have to be careful as to what high probability bound you get. Yeah.
Is it known how to get the KL divergence bound?
So for KL divergence bound, I will use this UCB version will not get it. To get the KL divergence is something called KL UCB, where you have to modify this term to incorporate a KL divergence term. So you have to, this is too much boost basically. So you have to make a tighter upper confidence bound, which relies on KL divergence. So there's a word called KL UCB where they do that. Also, then you have to assume something about the form of the distribution. So you can do it for Bernoulli or something. So the scale divergence doesn't depend just on the mean. Yeah.
Something for shown us that it's the end for regret is there without T or not yet?
No, not yet. Yeah, so this is instance specific bound. So from here, I just get, yeah, I reserved it for if someone will ask. So, so let me do that. So if you get this, so we have this bound so far. So now you can kind of, it's kind of unintuitive because you are saying that it's bad for an arm to have a small delta I, right? So you're saying that delta I, if it's too small, then this regret blows up. Whereas if you think about it, small delta I seems to be great. It means your arms are almost optimal. So you should not be suffering by making mistakes. So you should have smaller regret. So the reason it's happening is because small delta I makes it difficult to learn because it's hard to distinguish between optimal arm and the suboptimal arm if delta I is small, but you have less regret though. So to get a worst case bound in this case, you have to kind of divide it into two parts, saying that, okay, where is that border where it's not enough, like not so close that you can ignore it, but also close enough that you have to just make it hard to distinguish it, right? So that borderline seems to be, okay, let's call let's say delta I, let's look at the arms with delta I less than square root n over t. Okay, so and delta I greater than square root n over t. So these ones we will ignore, right? So we will say that all these are almost optimal. So the total regret of these arms can be bounded, even if I don't even care how many times they were played, even if they were played all the time, the total regret here is square root nt. And yeah.
So I have a question about the previous proof.
Can I finish?
But you can finish,
Yeah,
of
yeah.
course.
So the total regret here is square root nt from these arms. Okay. But for these arms, I will say that I will use this regret. So I'll basically count all these arms as optimal and then substitute delta I as at least this much here and get this expression will become then square root nt log t. So if I substitute this delta I here, I will get square root. Okay, maybe I'm missing a log t here. Yeah, log t. Yeah. So I will get a
Or your lower bound didn't have to.
yeah. So there is some work more recently on removing this log t. I don't know if someone will discuss it, but yeah, there has been some chasing of that log t in the literature. Yeah. And I believe they have removed it, right? So Bubek has a paper, or does anyone knows? Yeah. All right, yeah, your question.
So that hyperability was 1 minus 1 over t squared, right?
Yeah.
It doesn't depend on the number of arms. If you have a lot of arms, isn't that an issue that like you're going to get an error in some?
No, because it's t squared. Yeah, I'm assuming n is much smaller than t. Yeah, if you want to consider a
So you
change
need
where
some-
n is larger, then you might want to have log nt or something. Yeah. All right. So let's move on to the next one, Thompson sampling, which some of you might know is my favorite. But so this is a heuristic. So it's kind of a Bayesian heuristic. So it's more generated from the setting that I discussed in the beginning about the Bayesian way of learning. But we have kind of now adopted it to our prior free setting and kind of as an algorithm for the prior free setting. So the origin of the heuristic is Bayesian, which means that you kind of do the same thing. So you start with some prior about the arm distribution, and then every time you see the reward, you update the beliefs in the Bayesian way. And one of the main differences, instead of trying to compute the optimal policy like Gittin's index does, which is very hard in most cases, you simply pull the arm with its posterior probability of being the best arm. So let's parse this sentence a little bit because often people read it wrongly. So when you have Bayesian posteriors, what is the common like machine learning way or the Bayesian optimization way of doing things is you can compute which is the most likely to be the best arm according to the Bayesian posterior, right? So maybe according to the Bayesian posterior, the probability of first arm to be best arm is 90%, the second arm to be the best arm is 10%, and so on. So the maximum likelihood way would be to say that play the first arm because it has 90% probability of being the best arm. Here we are saying play the first arm with 90% probability and the second arm with 10% probability. So we are exploring by giving every arm a chance proportional to its chance of being the best arm. So even if an arm has 1% probability of being the best, you still play it with 1% probability. Okay, so it's very different from maximum likelihood choice. Okay. So what we will do is we will take this algorithm, but we will not assume that we know the prior. We will construct our own prior. So we will choose a prior which is very less informative, for example, uniform distribution, and then we will similarly evolve the posterior and play every arm with its probability of being the best arm. So for us, this will be the posterior will be a way to manage information rather than actually knowing that this is the posterior distribution of the reward, right? I hope that that point is clear, because that point is sometimes confusing. So what we will do, we consider two versions of this algorithm. So when we know that the reward is either 0 or 1, when we have a binary reward, in that setting, it's very convenient to have beta distributions as the posteriors, because they are conjugate to Bernoulli rewards. Okay, so in that setting, this is a convenient setting where you start with a uniform distribution, which is same as beta 1, 1. So beta distribution, if some of you haven't seen them, is this 2-parameter distribution. I plotted a few here, alpha and beta. So alpha is so larger alpha means you have more this to this side, the probability of being 1 is higher, and smaller alpha means you're on to this side. So you can see that alpha 2, 5, which is the orange one, is smaller alpha is on this side, and alpha 5, the blue one, is on this side, right? Like the peak is on this side. So larger alpha is good in some sense. You get more reward. Sorry? Sorry?
You remembered something about duality.
I didn't.
You said it's dual to Poisson.
Conjugate. Oh, it's conjugate to Bernoulli. So which means that when you write the Bayes rule, the posterior given a beta prior and a Bernoulli reward observation, the posterior is also beta. So it's conjugate to Bernoulli. So in particular, the update is really easy. If you start with a beta distribution with parameters alpha and beta, then you observe a Bernoulli reward of 1, then posterior you can calculate is simply the same beta distribution, but with alpha parameter increased by 1. And if you observe a 0, then the posterior is simply the one with beta parameter increased by 1. So it's very simple update. In general, a posterior distribution may not belong to the same family as the prior, or it may not even be analytically like a parametric distribution that you can write easily. So you might have to do methods like MCMC to simulate it and so on. But here you can very simply generate the samples from the next posterior. Okay. So given this setting, the algorithm becomes really simple. Basically, you start with uniform distribution for every arm, which is beta 1, 1. And then for every arm, any point, you know what the posterior will be. So whatever number of successes or ones you have observed, that will form your first parameter, because every time you observe the 1, you increased alpha by 1. So at any given time, your first parameter will be the number of ones observed for that arm and the number of zeros observed for that arm, plus 1, because we start with beta 1, 1. Okay. So at every time, this is the posterior for a given arm I. So you simply generate a sample from that posterior for every arm and play the arm with the maximum sample. Now, this process of sampling, I never mentioned it in Thompson sampling. This is simply to simulate that sentence that play every arm with its probability of being the best arm. So instead of computing the probability that beta distribution of I is more than beta distribution of every other arm, I simply simulate that line by saying generate a sample from everyone, and the max has the same probability of being I has the same probability of having the highest max as the probability of I to be the best. Okay, so I'm just simulating that line. Okay, so this is the Thompson sampling for beta distributions and Bernoulli rewards, and you can see as it's as simple as UCV to simulate basically. Now we don't want to restrict just to 0, 1 rewards, so there is a version that you can use for general rewards, which is with Gaussian. So we start basically with standard Gaussian, so mean 0 and standard and 1 standard deviation for every arm. Now, this is something we assume for deriving the posterior. This assumption doesn't have to be satisfied for the regret bounds. For regret bounds, it's enough to have a bounded distribution of rewards. Okay, so if you assume that the arm has a Gaussian likelihood, with mean mu, some mean mu and standard deviation, then you can see that the posterior after observing n samples is simply going to be, again, writing the Bayes rule. It's a Gaussian, has a conjugate prior for Gaussian distribution. So posterior will simply be the empirical mean for those n samples as the mean, and the standard deviation will be, variance will be 1 over n plus 1. Okay. So this is something you can derive using Bayes rule, and that observation we use to write this algorithm, which is we don't start with a normal prior, we start with some boost to the normal prior. This is like a logarithmic boost. And the reason is technical for the proofs, but we start with this normal prior, and then every time step, the arm i's posterior will be the empirical mean as the mean, and 1 over, and standard deviation proportional to 1 over the number of trials that arm has seen. So now the algorithm is simply sample a sample from every arm and play the arm with the maximum sample. So you're simply replacing the upper confidence bound by like a sample from the distribution with the mean roughly the same as what you had in UCB, but now you have instead of finding like one point here as UCB, you are generating a sample from this distribution and then playing the arm with the highest sample. So one reason that this algorithm generated interest almost 10 years ago was that sometimes, in some cases, instead of using this extreme point to make your decision, using something around the mean can be practically result into less exploration, like wasting less time in exploration. And this was observed empirically, and therefore we wanted to analyze the regret of this algorithm. The algorithm itself is very old, and there's not much chance of improving the regret beyond UCB's regret because UCB's regret is almost optimal already, right? So we don't hope to improve the regret, but the hope was that you can show that it also has a good theoretical properties in addition to the practical properties. So the regret bounds for this looks like this. So first of all, for Bernoulli rewards, in fact, the basic algorithm, so this was like really nice observation that even the basic algorithm without doing any modification gets you the right KL divergence term under it. So the intuition is that because you are not making up these confidence bounds, like it's not an upper bound, it's really posterior captures all the information you have about the arm and nothing more and nothing less, right? So it gets you the right term here in terms of KL divergence, the bound. So it's logarithmic bound like UCB, but the constants are slightly better in terms of KL divergence. So instead of 1 over delta I, you have delta I over KL divergence. And the other case, which is Gaussian prior. So if you don't have Bernoulli rewards, if you have just general bounded rewards, you have to use the Gaussian version of the algorithm, then you can get same as UCB basically, log T over delta I. And you also get the same worst case bound. Okay. So I'll discuss next the proofs of Thompson sampling a little bit, unless you have some questions before that. Yeah.
So you act as if that's the Gaussian prior, but then say it's arbitrary bounded performed.
Yeah.
It sort of indicates that maybe if the form's not bounded but has fast enough tails, it still should work.
Yes. So all these results are extendable to sub-Gaussian results, unbounded sub-Gaussian results. Yes. Yeah.
Just to make sure I understand it, you're saying that the key advantage of Thompson sampling against UCB is that you get slightly better dependence in the regret. Is that what? I
mean, theoretically, yes, although you can also modify UCB, like to have more complicated upper confidence bounds in terms of KL divergence. Like if you know you're dealing with Bernoulli, and then you can modify your confidence bounds a little bit to get the same bound. So I won't say like, I wouldn't infer that's the main advantage. I mean, it kind of happened the reverse, that it works well, and then you want to analyze it and show it also has theoretical properties.
So do you view the main advantage is that empirically it works better? I see.
Yeah.
So the epsilon term, the 1 over epsilon squared term, so I guess divide by log T by integral. Is there any factors you get closer? Extra term that blows up?
So usually people don't even write this. First of all, I'm being very, very technical here to write this. So like, for example, if you just make this epsilon 1, we can just ignore this part. Because it just makes the constant as 2. We wrote this because then it matches exactly the lower bound. So lower bound says like you can get arbitrary close to 1 if you allow this additive term. Like this, because this additive term doesn't increase with time. So that's why it's significant, right? So this term increases with time, this doesn't.
That's my question.
Yeah.
So divide by log T depending on how you take the limits, I guess.
Yeah, so it depends on how much you are comparing n versus t, I think. Yeah, whether n is logarithmic in time or it's constant compared to t. Yeah. About significance, I want to mention one more thing. The reason I like Thompson sampling is because it's easier to design, I think. So it's like you don't have to design confidence intervals. Like if you want to implement a Thompson sampling algorithm, you just compute the posterior sample from it. For every extension of the problem, you don't have to compute confidence intervals and carefully think about what the constant should be and so on. Yeah.
Are these Bayesian requests?
No, these are worst case. Yeah. No prior knowledge. So we start with a prior which is non-informative, like uniform or standard Gaussian, which may have nothing to do with actual distribution. Okay, so what is the idea behind proving such a bound? In this, why does this work? So we kind of understand intuitively why does upper confidence bound work. So why do we even hope for this to work? What is it doing that will allow us to capture exploration versus exploitation, right? So the idea is that you are maintaining these posteriors, and these posteriors are capturing exploitation in their mode or their mean and exploration in their spread. Okay, because posterior distribution is not a one-point estimate, it's an entire distribution. So it's telling you not only what it believes to be most likely to be the parameter, but it also telling you how uncertain it is about the parameter. So the blue distribution, for example, it says the most likely estimate of the parameter is here, right, which is slightly worse than the red one. But it also saying I'm actually not as certain as the red one. It can be anywhere with a very good probability. It has a very wide range of of how much the parameter could be, right? So it's telling you more information than just what the estimate. It's telling you both about the uncertainty and the most likely estimate. So the idea is if we sample from it, then if a distribution has a lower mode, lower likely to be the value of the parameter, it could still have a higher sample because you are uncertain about it. And that will provide you a benefit of doubt to an arm for which you are uncertain about by sampling from the more spread. So the spread will enable exploration, whereas the mean or the mode will enable exploitation. So let's see how that idea shows up in regret calculation formally. So let's look at just 2-arm example to keep it simple. So you have 2 arms, and again, I'll assume arm 1 is the higher one. Of course, the algorithm doesn't know that. And the delta regret of playing arm 2 instead of the optimal arm is mu1 minus mu2. So there's only one arm, there's only one delta. So overall, to bound regret in this simple case, you want to show that the number of pulls of arm 2 is bounded by log T over delta square. So sorry, I will not be able to show the KL divergence version of the proof, but the idea is the same. Okay, so I want to prove log T over delta regret by showing that the arm 2, the bad arm, will not be pulled by more than constant times log T over delta squared. Okay, so how many pulls can happen? So I will kind of divide the whole timeline into 3 parts. And the easier part of the timeline is some point, which is a random point. I don't know when it will happen, that when both arm 2 and arm 1 have number of pulls more than some constant times log t over delta square. So this is both n1 and n2. So after this happens, and I don't know when this time will happen, but whenever this happens, after that, I'm golden. Why? If both arm 1 and arm 2 have been pulled enough times, which is that much, then both of them will have a very highly concentrated posteriors. Why? Because the posteriors, as we saw, like in beta distribution on both in beta and Gaussian, the mean of the posterior, for example, in beta is this, and this is exactly mu hat, basically. Okay, and same way in Gaussian. So mean is the empirical mean, and you can see once you have this much place, like in UCB we talked about, the empirical mean will be very close to the actual mean. In fact, the exact calculation can show this will be less than, in this case, like delta by 4. Okay, and then so this is that, but so empirical mean is close to the actual mean, so that's the mean of my posterior. But what about the spread? The spread in both beta and Gaussian is actually 1 over alpha plus beta, which is number of trials of the arm. Okay, so now the number of trials, once it is that, again you can show that the variance is 1 over n, so that will also give you that the spread, the standard deviation 1 over square root n is also less than delta by 4. Okay, so this gap here is also less than delta by 4. So the total gap, which is delta, right? So you can show that because the spread and the error in the mean both are less than delta by 4, the two arms will be separated completely. Like by separated, I mean the overlap between them will be very, very small. So overall, like basically we are saying once both the arms have had enough number of samples, both will have some peaked posterior, so you cannot confuse them when you take samples, because samples from here would be higher than the samples from here. So this is a nice picture you'll get once both of the arms have been played. Now this is problematic because you remember in UCB we said, oh, we are golden after bad arm has been played enough, and because if bad arm has not been played enough, anyway regret is small, so we are done, right? Now this is here I'm saying no, not just bad arm, I'm saying both the arm have been played enough. But before that, what about the regret before that? I cannot say the regret is small here because I have to wait for even the good arm to be played. And by that time, bad arm might have been played a lot. Okay, so I have to bound this regret now. Okay. This is the problematic area because exactly this situation, maybe the bad arm has been played enough already, but the good arm has not been. So the bad arm, we are waiting for the good arm to be played enough. And by that time, bad arm might have been played a lot more times and we accumulate a lot of regret. So how long will it take for the good arm to be played? So now let's look at this middle point. So we are also golden before N2 has been played enough. Okay, so let's consider this point as the point where N2 exceeds its place. Okay, so we can wait till this point because until this point, there is not much regret anyway. Okay, until bad arm has been played. So we can wait till this point, but how long will it take to go from here to here when we get good arm to be played? That is our concern, this middle portion, okay? So we are in this middle portion means that bad arm has been played. The red arm has a good concentration, nice peaked posterior, but the good arm is all over the place. How long does it take for good arm to go and be here, okay? So what is this situation? Here, the problem is there are two problems because we are not doing UCB, we are sampling. So it can happen because the good arm has this huge spread. First of all, its empirical mean could be bad. Even if its empirical mean is good, it could have a huge spread and we could be sampling from below the actual mean, much below the actual mean, and therefore not play the good arm. So what we'll show is that this middle portion, this bad portion, we can quickly go through it exactly because of the spread of this arm. So because of the spread of this arm is actually useful. Why? Because the spread allows it to be randomly played sometimes. Not very often, but at least constant probability. Because its spread is so huge, it will, yeah, with constant probability, it will fall below, but with constant probability, it will also fall above. So every constant number of steps, I will play the good arms. Okay. And constant number of steps is not good for regret, but it is good enough to get out of this situation and get this many plays. Because it means to get this many plays, I only need constant times that many steps if I'm being played every constant number of steps. Okay, so this is basically the idea. We show that because of its spread, until the arm one reaches its peak, enough number of plays, it has enough spread to be played roughly every constant number of steps. And so to get log t over delta squared plays, it only needs constant times log t over delta squared steps. Okay. So after that, we will reach that golden place where both arms have enough plays. Okay. And of course, this constant is all roughly speaking. You actually get better and better as you play, so you can get tighter bounds. You can have better things here than constants. Okay. So that's the idea. And you have to get tighter bound exact constants and so on. You have to do more careful analysis. But what I want you to remember is that the variance of the posterior, the spread here, exactly what enabled exploration of the good arm, right? Because of the spread, the good arm was played every constant number of steps and get out of the situation, the bad situation, right? So when you want to do multiple arms, this doesn't work exactly, I said, because now you don't have this nice 3 partition of the timeline, because you have to wait for all the bad arms to be played. And you cannot say, okay, when will it happen that all the bad arms, like you cannot say, let's just wait till this point when all the bad arms are played, because that might take a long time for all the bad arms to complete their plays. So you have to be careful in that case. And we prove this very nice inequality, which is the key to the whole analysis. Should be I star, sorry. So the key to the analysis to show not that the good arm will be played every constant number of steps, or it has a constant probability of playing, but saying that good arm has a constant probability of the probability of playing any given bad arm. So it's not that it just has a constant probability. It's compared to every bad arm, it has constant probability, which means that every time you play a bad arm, like every time you get charged for a bad arm, you also get a point for a good arm, like a constant times that point for a good arm play. So you kind of can do this charging argument where you can get enough number, like every time you suffer a regret for playing a bad arm, you also get like information about the good arm. So you kind of can show that if you accumulated enough regret, you also have gotten enough plays of the good arm. So I think I'm almost out, I'm out of time. So we can take a few questions and then take more questions in the break. Yeah. Yeah.
Is there any unifying view of usage distribution of the confidence bound that shows more?
Yeah, I have not done that kind of thinking, but I saw something related to this at various points. Yeah, I'm sure like you can make a distribution like that and try to randomize over that distribution instead of the posterior that they designed and then come up with an explanation like this.
Just pick the uniform distribution
over the confidence interval. I don't think uniform will work. We give too much probability to the center one. Yeah, I don't know. Yeah, I don't know if it will conceptually gain anything to do the analysis, but yeah, I guess, but for curiosity, it was good. Yeah. Yeah. Well, yeah.
So you talked about the sort of expected regret today.
Yeah.
Are things known about the distribution of regret of the two algorithms and if they differ?
Yeah. So for many of these things, you can prove even like a. So there are two things. But if you want to prove high probability regret, but you still define regret as. But if I still define regret as in terms of the expected values, you see my point. Like if I still define regret as the mean, difference,
Okay.
right? But I remove this expectation, then I believe you can get high probability bounds. If you want to define the gradient in terms of actual reward, then it will start depending on the distribution of the reward, not just the mean, right? Because it will depend on the variance of the actual distribution. But I think it should still be possible by using high, like if it's bounded distribution. So.
And is it known if one of UCB or Thompson is like more variable than the other?
I don't think theoretically there is any difference, but empirically, then. At least I don't know what the research is about.
You mentioned that empirically Thompson sampling works better than UCB. So does this universal phenomenon maybe across the different number of arms? So when you have small number of arms, when you have.
So yeah, again, this is the empirical statements are always subject to conditions under which it was tested, and I'm sure there are conditions in which UCB works better. But I have seen it in, for example, my own experiments on the problem I talk about in MNL, which is assortment optimization. It was very, very visible. I mean, there are sometimes you can like play around with the confidence interval of UCB to make it tight enough to get it right, but then you need to know, like it's usually in hindsight, it's like hard to tune it. So I would say, as I was saying before, even if you can tune it to be really good, I think the advantage of Thompson I found is it requires less tuning. Which could be very important sometimes, right? And there were some experiments in the original paper that inspired us by Li Hong Li and Oliver Chappelle. They had experiments showing in the case of linear contextual bandits that there was significant difference between the empirical performance. Again, one could argue that the confidence intervals they used are not tight enough, and so it's best apart kind of design. Yeah.
I guess it's related to the earlier question. How sensitive is the proof to Bayesian updates? Like, can you prove something like, as long as you do uncertainty quantification in a reasonable way, you get reasonable regret?
So you can kind of, again, because the differences between these algorithms is more conceptual rather than actual, because you get the same degree bound and you're kind of randomizing over. So if you keep doing that, you can almost do like a randomized CCD. Right. So and then like I think something similar to what Jack was asking. So in the assortment optimization work we did, the posterior was very difficult to calculate. So we approximated it by something like an uncertainty quantification to avoid doing the NCMC sampling, for example. So once you do that, it becomes closer and closer to UCB.
Oh, you think the reasonable meta theorem is true?
The meta theorem?
Like, let's say, as long as you do uncertainty quantification in a somewhat reasonable way and you're somewhat optimistic, you get good regret.
I don't know of any like such general result, but I would say, like as a folklore knowledge, it should be true.
Okay, if like me, you'll enjoy that a huge amount. The good news is we have more of Shipra after this, so we have 1 more hour from. So we have a break right now, and we should come back before 11 just so that we can have as much more of this tutorial as possible. So feel free to. I think there should be some refreshments outside, and at 11 we assemble.